Okay, so first things first, can you hear me? You guys should have a chat feature and you can send messages. I can't hear you guys, but you can send me messages and I can read them. So if somebody wants to be the brave soul to test that, that'd be pretty awesome. Oh, all right, cool. Okay. Oh, they even get your whole name. You guys have your whole names on here. That's pretty neat. I wasn't expecting that. You guys are troopers showing up to a live stream on a Wednesday night that was supposed to be a snow day because you have a test tomorrow. So kudos to you. Oops, that's the wrong pin. Oh, Warren. Oh, you guys are going to be fine. Yeah, there's also an exam recovery assignment. So if he lets you guys get some of your points back on the multiple choice questions. So for the free response, he's just really generous with the partial credit since you guys are going to show your steps there. And then for the multiple choice, you just get a grade for whether or not you pick the correct answer, but you'll be able to earn some points back at a later date, usually the week after. It gives you about a week to do the exam recovery assignment, so you'll turn that in about a week after you get your test back, and you can get some points back on that. So don't be too worried about it. You guys will be just fine. All right, you guys are doing a great job of scanning the QR code when you join the stream, so just keep that up. That's fantastic. And that's so we know that you guys like this. This is a little bit experimental. I've never done this before, so hopefully this works out. The link is also posted on Blackboard, so if the QR code doesn't work, you can just click the SI session sign-in link on Blackboard and it'll take you to the exact same survey. Yeah, so during this kind of awkward period where we're just kind of waiting for 6:30 to happen and letting you guys get scanned in and adjusted to the weird technology, if you guys have any questions, you can put them in the chat and we'll just kind of Q&A this first chunk if you'd like that. So we can, talk about like test stuff or what's going to be on the test or test structure, that kind of thing. If you guys want, we can talk about that until we get started. So just put stuff in the chat. There is a little bit of a delay, so I might not answer something as soon as you put it in because it has a little couple second delay there. But how many questions? I'm not entirely sure. Last semester, I think it was like 3 free response, but that and 2 multiple choice or something like that. But I mean, again, that was last semester. He had 50-minute classes. You guys have 75 minutes, so I think it's going to be an extra question or two to account for you guys having extra time. And he sent out that email this morning that if you take about 2 problems from each homework assignment, you would have a pretty decent length practice test. So I would say that's probably a good indication of how long the test will be. One. I think so. It looks like last semester the test was 5 questions. So this semester probably 6 or 7, I would think, is a reasonable number, considering you guys have extra time. But that's a good thing because that would mean that each question's worth a little bit less points overall. So if you really screw up one of them, you would have less points deducted than if you had done that on a test with less questions. The format, so there will be a mixture of like free response style questions where you will get to answer pretty much whatever you want, which is what the questions are on the test review set packet that we're going to go through today. And then you'll also have a couple multiple choice questions where you still want to work out your answers, but he'll have like 4 or 5 answer options for you to choose from, and you'll choose which one you think is correct. And for those ones, so for the multiple choice, you'll get all or nothing credit. It's either you chose the right answer or you didn't. Someone has asked me previously if it's like chemistry. Apparently in chemistry, you could have like A, B, C, and it like permutates how many options you have. It's not like that. It's just a straight up A, B, C, D or A, B, C, D, E, and I'm not sure. I don't remember exactly how many options he gives you. So that's all or nothing credit. And then he's pretty generous with the partial credit on the free response part. So make sure you're showing your work. Okay, so Bethany asks, what conversions, factors, constants should you know? So I would say probably anything you don't just know off the top of your head. So like if you know, like I know that G is 9.8 meters per second squared off the top of my head. I might not write that on my index card, but anything that you feel like might be on there, it doesn't hurt to put it on there. He doesn't care what size the index card is. So as large of an index card as you can buy, you can use. Someone last year had index cards the size of literally a sheet of paper cut in half is the size of his index card, and he wrote all over it front and back. So you can put anything you want on there, so don't be too concerned about space. I would say, you may not need, I'm not sure if you would, for the most part, whatever units are in the problem or what units your responses are going to be in. So I would say you probably aren't going to need to know like how many meters are in a mile, because he's probably going to just either give you the question in meters, expect answers in meters, or give you miles, expect answers in miles, if that makes sense. So I don't think he's not going to throw you guys just oddball conversions just to see who put the conversion factors on their index card. I would recommend, if you're not familiar with the metric prefixes, you might want to put some of those on your index card. So if you don't just know off the top of your head that kilo is 10 to the third, stuff like that, you might want to put some of those on there just to have them. Does that answer that question sufficiently? Okay, Warren asked how my day was. My day was pretty good. I hope you guys all had a good day. You can put smiley faces if you're having a good snow day. You probably liked having the whole day to study for physics instead of having to go to class, so that's pretty cool. John asks, how do test questions usually compare in difficulty to the problems on the review packet or the practice problems? Are you talking about my review packet or the problems that he posted? Your guys' homework and problem sets are about the same difficulty as your test questions are going to be. He doesn't just completely amp up how difficult things are on the test to make it like really difficult on purpose. You know, it's pretty much the same type of material you guys have been doing. The main difference with the test is that, you know, for your homework, you have as much time as you want to work on it, whereas for the test, you are under a time constraint. So I would say the difficulty is probably the same. It feels a little bit more stressful because you're under that time constraint. There's a little bit of stress involved with test taking. All right, and you guys are doing a great job of scanning that QR code as you join, so keep that up. That's really awesome. Yeah, and don't forget your index card. So if you haven't made your index card yet, go ahead and do that tonight because that's pretty important. You get to have that, so use it to your advantage. Does Banerjee's test differ from Chastain's? I have no idea what Dr. Banerjee's test looked like. I've never seen one. So I have no idea, honestly. I can tell you because I did SI for Dr. Davis before, that Dr. Chastain's tests are quite a bit easier than Dr. Davis's test. Dr. Davis does full partial credit questions, which is great, but he also doesn't let his students have a calculator or an index card. So that makes it pretty difficult. Are you going to get the answers to the homework problems? Well, I'm not sure if he posts homework solutions or not. So I'm not sure about that. I don't have anything to do with the homework assignments. I kind of just do my own thing over with the SI stuff, and I don't really do much with the homework unless people send me questions about it. So I don't know the answers to those off the top of my head because I haven't worked all of them. But I would say probably you could ask Dr. Chastain if he'll post those or let you know. You guys should have grades on those. I think some of them at least. I should probably shrink that a little bit. There we go. I didn't even realize I had the bottom of that cut off. What if you get off tomorrow? So U of L already sent the alert out saying that classes are in session tomorrow. So it's highly unlikely that they will change their mind on that. Because they said open and on regular schedule. That went out about 3:30 today. So if there's no class tomorrow, then Dr. Chastain will send out an email with what the next steps are. I would assume that that would mean your test would be on Tuesday, but right now plan on it being tomorrow. Luke says he said in class he was not going to post answers to homework. Yeah, I'm not really surprised by that. I'm not sure what I don't know how you would get them then. Oh, don't cry. Yeah, I would say, maybe you guys can use each other as resources. Like maybe if you know that you got a number 2 wrong on the homework or something, you can maybe find a friend who got it right and see what their solution looked like. So you could try that maybe. Or you can email it to me because I can take a look at it and tell you if it looks right or not. And I can kind of look at it, like whichever one you've got a question on. I just I haven't sat down and like worked all of your homework out. So I don't actually know what the answer. I don't even know what half the questions are. But if you send it to me, I'll take a look at it. I just won't be doing that until after 8:30. I don't have an Instagram. So I would follow you, but I don't have an Instagram. I'm sorry. I'm not cool enough for that. Oh, okay. So your test questions are probably they're going to be about a similar difficulty to your homework problems or your problem set problems. The main the main thing that just makes the test more difficult is that you're under time constraints. Like on your homework, you have however many hours you want to spend on your physics homework. On the test, you have 75 minutes to do, I think we have like 6 or 7 problems or whatever. I think typically, from what I understand, you guys' recitation problems, at least towards the end of the semester, some of them are more difficult than exam questions because you guys will spend like the whole recitation working on one question. So I would say those are probably not as good of an indicator. I'm not sure if that's the same for these units because I haven't seen the recitation. I don't go to recitation. But the homework problems and the practice problems, the problem sets that he posts, those are a good indicator of what kind of questions you'll have on the exam. Can we do every SI session like this? I don't think so. If this goes really well, we'll see about maybe recording them or something. We can look into it. This is epic. Okay. I don't know. We can look into it. I mean, right now, you guys, if you guys express a lot of interest in doing this again, I'll definitely talk to Reach and see what they'd like to do about it, and maybe we can work something out, even if it's just for future exam reviews. But, I'm not opposed to it, so we'll see. And you guys are doing a really great job of scanning that QR code as you join, so just keep that up. This is really great. This is good. Oh, well, I'm glad you guys like this. Thank you. This does make it a little bit more difficult as far as answering questions and stuff go, because once I start writing, the chat feed is actually on my desktop, and I'm using my laptop with OneNote so I can write on it. So I'm going to have to go back and forth. Now I know who Warren is. Warren, I now know what your face looks like. I highly doubt that. Yeah, and then there's no sound, so I can't actually hear you guys talk. Which, I mean, but it would be kind of obnoxious if I could, because there are apparently 38 of you watching this, so 37. Someone left. uh, it's a snow day. I mean, yes, you are using the Engineering 110 account. All right, it's almost 6:30, so keep scanning the QR code. That's pretty awesome. You guys are doing pretty good with that so far. We're only missing a few. So if you haven't done that yet, go ahead and do it. If you're having issues with the QR scanning, the link is posted on Blackboard under the supplemental instruction tab. You can just click the sign-in link, or you can just send me an email and say that you watched it, but you couldn't scan, and then I'll have a record that you were here. All right, so we'll just give it a few more minutes for anybody who clicked the link right at 6:30 to get in, and we'll start in a couple minutes. All right, does anybody have any other preliminary questions before we get started that you would like me to answer? You're watching this at Vilgrill? That's great. Dr. Chastain did not give me this material. This is mine. I made it. He has seen it, so he knows that it's like accurate and stuff. It's posted on Blackboard. He has access to it as well. This is also mostly the same review that I went through last year with his class. So he trusts my material for the most part. He's been able to see it before. But this is not from him. So if you are going through like his practice material on Blackboard, this isn't going to duplicate that. Okay, all right. So first things first, if you go to Blackboard, let me find Blackboard. I have it somewhere. Blackboard. So you'll see, oh, this isn't updated. Hold on. All right, so on Blackboard, you will see your class here, and then there's the supplemental instruction tab. So here's our live stream information here. And this is the review packet that we're going to go through right here where it says attached files. So if you have not printed this out yet, you can pull that open and put it in OneNote or something if you want to write all over it, kind of like I am. Some of you printed it out earlier. I posted that earlier today. And that's where the packet is that we're going to go through. Most of you already found the link or you saw it in the email. Here's the sign-in link if the QR code does not work. I'll put the QR code back up for those of you who have not scanned in yet. So go ahead and do that and we'll get started in just a minute. All right. Okay, so again, if you were not able to scan it on the QR code yet, the link is on Blackboard, or you can just send me an email and let me know that you watched this. All right, and here is the packet. All right, so firstly, we're going to just do some review of concepts. That's the sign. What? That's the sign-in link. Did I miss a message? I don't see something before that. Okay. So we're going to just review kind of some concept stuff about like how do we work these different kinds of problems? What are the Oh, you sent oh, I didn't see you send a link. I'm sorry, Warren. I didn't see a link. All right. So we're going to go through what the steps are to solve different problems, and we're going to go through some of our equations or other various information that's important to know on the test. And the idea here is that if you kind of take these review questions and the answers that go to them and you put them on your index card, you're going to have a really nice guide to get you through the test. So we're going to go through that first, and then I'm going to show you my example index card. All right, so first off, the steps to solve a vector problem. So vector addition or subtraction. Our first thing really for every problem is that we're going to draw a picture, right? So Dr. Chastain's really big about drawing a picture. It helps us visualize what's going on in our problem so that we can better solve our physics problem, okay? So after we've drawn our picture, then we're going to draw a vector diagram. And in some instances, the picture and the vector diagram will end up being the same thing, and in some instances, they won't. Okay, so your traditional vector diagram is when you have your vectors coming from the origin out in different directions. Okay? And that's the one that we use when we set up our table, which is step 3. So step 3, we're going to choose our axis. So we're going to pick our x and y axis, and we're going to determine which sides we want to be positive and negative. All right, so we're going to choose an axis. And we're going to do our table. All right, and I apologize for my slightly atrocious handwriting. I have very bad handwriting on the tablet. All right, so after we have chosen our axis, then we can use that information and where our vectors are on the diagram to set up our table. And that's where we're going to be really careful breaking things into components and making sure that we get our sines and cosines in the right places. All right, and after we have done that, then we can write equations for our x and y directions. And we can use those equations to then solve for unknowns. And once we solve for, and, if you're doing a traditional addition problem or something and you're solving for what your x component of your resultant and the y component of your resultant are, then you can take your x and y components and you can Pythagorize and you can do inverse tangent to get your angle, right? And that's what's going to be your final answer. And Pythagorize is just that invented word that Dr. Chastain likes. It means we're going to use the Pythagorean theorem and we're going to square our x component and our y component and add them together. All right, so that's all that means. And then we just inverse tangent our angle. And remember that whatever value you put in the denominator when you do that tangent, that inverse tangent, that is the axis that your angle is going to be with respect to. And that's also the axis that we use for cosine, right? So when you have your angle and it's touching an axis like here, see that's touching the x-axis, so that means that the x component will get the cosine of that angle, and that is the one that goes on the bottom of the tangent function. So if you're looking to get your equation with respect to the y-axis, then you would put your x component over your y component. Ethan asks if we are using kinematics on the test. We are not. So kinematics has been omitted from the exam. That will be on exam 2 now. So we are just going to be doing vector addition and subtraction and Newton's second law problems. And that's what we're going to review today. Now, average kinematics is on the test. Average kinematics is when you're looking at like your velocity versus your speed. And those are going to be generally included with a vector problem, which is what we'll see as we continue with the exam review. But you still need to understand the basic concepts behind velocity and acceleration for this exam. All right, so that's our steps to solve a vector problem. And again, if you have questions, just put them in the chat. Do you need to write equations on your card? Yes, you want any equations that you think you're going to need, any equations that go with this, or equations or formulas, yeah, any that you think go with these units, you would want to put on there. The kinematics piece, you won't need to know. So those 4 equations that are on that flow chart that he gave you in lecture, the flow chart from the slides, you don't need those for this test, but they will be on test 2. Yeah, so your main equations this time are basically going to be your F equals ma. I think that's really probably the only one that you guys will actually use. So you need to know that one. And then if you want to have any kind of information about how you do your vector tables and whatnot, you can put that on your index card. Okay, so when we break a vector into components, we are looking at that vector and we're looking at its angle. So we basically have 2 main kind of situations. I'm just going to draw them kind of the same way here. And this we kind of touched on a little bit just now, but so like if that's your axis, so you could have your angle touching the x-axis, or you could have your angle touching the y-axis. And if your angle is touching the x-axis, then your x component, so if we say that this is called r, then your r cosine theta will be your x component, and like this, and then you would have your r sine theta as your y component. Okay, how do you decide north, south, east, west for an angle? Yeah, exactly. Ethan, thanks for helping Mary out there. So you're just going to use your degrees and your X and Y components to figure out which quadrant you're in. And then depending on what side the angle is on the quadrant is the way that you put those directions. So if you want to see something, let's see, we can review that real quick. So if you got something like this, NESW, remember this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So based off of your, say you have your X positive defined this way, then if you've got a positive X and Y component, you're in quadrant 1, and then depending on whether the angle is down here or up here is how you would determine if it's east of north or if it's north of east. So whichever one the axis is touching, that's going to be the second letter that you say. So if you're looking at this one, this angle goes from the vector to the x-axis, so to east. So in this case, you would say north of east. Or if you were down here and your angle was right here, you would go to the south. And so now your angle is west of south. Does that make sense? All right. So again, the only thing that's going to be different on this side is that now our y component gets the cosine. And our x component will get the sine. Oh, it didn't pick up my r there. Okay. So once you get those figured out, that's a pretty easy way to do it is just whichever one it's touching is the cosine. And then in the same way, whichever one that it's touching, that's just going to be the second letter when you do your direction. So north of east, west of south, so it's touching that axis. All right. Any other questions on the north, south, east, west situation? Or are you guys good? All right. Fantastic. So average kinematics, so we just need to make sure that we understand what these different things mean. There are some common misconceptions here. So we're going to clear some of that up. So positive velocity, that just means that you're moving in the positive direction. It doesn't mean you're speeding up. It doesn't mean you're slowing down. It just means you are moving in the positive direction. So in the direction of positive X or positive Y. Okay, positive acceleration is what tells you that your speed or your velocity is increasing. So you are speeding up. All right, negative velocity, same idea. It just means that we're moving in the positive or in the negative direction now. Okay, so it doesn't mean you're slowing down. It just means that you are now moving in the negative direction. Negative acceleration just means you're slowing down. So velocity is decreasing. Right? If your velocity is 0, that just means that you're not moving at that moment. So if you're, paused or if there's just no movement happening, you're at rest. It just means there's no movement in whatever direction you're looking at. So think about like if you're looking at vectors, you may have movement in the y direction, but not the x. So the x component is 0 because there's no movement in the x direction, but you still do have movement in the y direction. All right, so just with respect to whatever direction you're looking at, you have no movement. Now, when acceleration is 0, some people want to say that that means you're not moving, and that's not necessarily the case. It could be true, though, but acceleration being 0 is only telling you that your velocity is constant, because that means, when you take the derivative of a constant, that is 0, and acceleration is the derivative or the change in velocity over time. So all it means is that you're moving at a constant velocity. That number could be positive or negative. It's just not changing. Okay, so it's true if your velocity is 0 and it's staying at 0, it's not starting at 0 and speeding up or starting at 0 and, speeding up in the negative direction. So now you would have a negative velocity after some time. It just means that you're not necessarily speeding up or slowing down. You're staying at a constant velocity. So it could be 0. But not necessarily. This is the future of it. Well, don't be mean to people in chat, okay? Don't say mean things. All right, again, if you're coming in a little bit late, if you go to Blackboard, you'll see the sign-in link here. So just click this sign-in link. Whoa, my pen just did a weird thing. So you can click this sign-in link to sign in so we know you're here. All right. Does anybody have any questions about that first part of review? All right. And all of you guys know Newton's second law, right? Because that's FMA, what you guys like to say. So F equals ma. And that just means the sum of the forces is equal to the mass times acceleration. And you can use that in different dimensions too. So you could just look at the y direction or just look at the x direction when you do that, which is what we're generally going to do when we break our table up. Okay? So the steps to solve a Newton's second law free body diagram problem. So first thing that we need to do is, if we're not already given a picture, which for some of these you may be given a picture, you need to draw a picture. And that's pretty much going to be step 1 for almost every problem for the entire class. Dr. Chastain's really big about drawing a picture. Okay, so part 2, you want to draw and label a free body diagram. Oh. And you want to do one of those for each shape, or per object, really. Better word. Okay, so like he said in class, 2-object free body diagram problem is fair game on the exam. Kristen asks, if you don't draw a picture, will you lose points? You could, yes. So, I mean, for some of the Newton's second law problems, you'll be given a picture and then you'll draw your free body diagram separately, and you would lose points for not drawing your free body diagram, at least from what I understand. And I mean, even if it weren't a point thing, you should want to draw a free body diagram because it helps you solve the problem. But for drawing the picture, it usually just helps you kind of visualize what's going on so that when you draw your free body diagram, it can be as accurate as possible. Chris, does attendance for SI sessions have an impact on your grade? It does not have an impact on your grade, but Reach needs to know how many people are coming so that they know it's worth it to have it. So if we don't have, like if there's not enough attendance, then they may not let me stay with you guys for the rest of the semester or something. And at the same time, we also use it to track statistics, because students who go to SI sessions regularly tend to get higher grades in the class. And those statistics are what they can present to get money to pay the SI leaders. So it's pretty important to like just how the whole program works. Oh, yeah, you got me on that one. I spelled label wrong. Thank you for that. I am an engineering major. Yeah, so please sign in so that I can stay with you guys, because I like staying with you guys. This is, I've done this for 5 semesters because I like doing it. So I would like to be able to stay with you all, and it'd be pretty awesome. So thank you for signing in if you've done so already. All right, so back to steps. So number 3, after we've drawn that free body diagram, we're going to choose our coordinate system. All right, and if you guys remember, he gave you guys kind of a hint in class. What do we look at to make sure we're choosing the right coordinate system? Right? There's a certain thing we're going to look at. It's the acceleration. I think there's too much of a lag on the chat for us to do kind of more like a question and answer thing. Yeah, there we go. Now you guys are putting it in there. Okay, I think there's just too much of a delay because it took a good couple seconds there for me to see anything pop up. But yeah, so you're going to look at your acceleration, and that's going to help you determine your coordinate system, because you want your MA, right? You have all your forces equal to MA, so whatever direction your acceleration is, that's going to be one of those equations. Right? So look at your acceleration to determine your coordinate system. And if you got to look at your acceleration, that means you should probably want to label it on your free body diagram. So you're going to put all of your forces and you're going to label your acceleration on that. Okay? So step 4, now we're going to make a table. And we're going to break our force vectors into components. Is projectile motion going to use Newton's second law? Well, I mean, technically you can have them both in the same question. So you could have like a box that you shove up a ramp, so you can have Newton's second law to calculate the acceleration when it leaves the ramp, and then after it goes off the ramp, now it's a projectile. So it is pretty easy to put those both in the same problem. But again, projectile motion's not going to be on the exam, at least not this first one. That'll be on exam 2. So you don't really need to worry about that at the moment. So Ethan, not quite. So acceleration in projectile motion isn't always the force of gravity. It is in the y direction. So in the y direction, you have that, but you might have something different in the x direction. Or if you're going off of a ramp, you're going to have some component of whatever acceleration you had in the x and y directions. It's going to carry over. All right, John asked, if we have to leave at any point during this, will we be able to go back and watch the entire stream later? I believe so. I'm not entirely certain about that, because I have never done this before, but I would say maybe. So do we have to draw a picture and free body diagram, or can we just write an answer and go all or nothing? Well, you should draw your picture and free body diagram, because you're going to get points for that. I wouldn't recommend just writing a number and like circling it on the test, because he's going to have no idea where you got that from. Oh, look at that. Keely has min-maxed it. Look at Keely. She said if you join late, you can go back to where the QR code is and scan it. That's pretty great. That's awesome. So if you haven't scanned the QR code yet, you should totally do that. It's pretty awesome. All right. So after we've broken our force vectors up into components, step 5 is we set up our equations. And we want 1 per dimension. So usually that's going to be the x and the y directions, right? So we're going to have an x equation and a y equation using Newton's second law with the forces in those directions. Okay, so after you get those equations, then you can substitute magnitudes where relevant. Okay, and the idea here is, for the most part with physics, you want to try to leave things in terms of like the letters or the variables as long as possible, and then put your numbers in towards the end, because if you make algebra mistakes while it's still the letters, it's easier for them to grade. So when he's grading your tests, generally it's going to be easier for him to give you that partial credit if he can see what went wrong with just that, and he can tell it was just algebra. So that's a good idea. All right, so Keely says on practice problems, half of the problem is just drawing the free body diagram. So I assume on the test he will count it for points. Yes, he will count the free body diagram for points, for sure. I'm not sure if it'll be like half of the points, but it is pretty big deal. It's pretty important to make sure that you have that drawn. All right, once you've substituted magnitudes, then you can solve for unknowns. That's our last step. So whatever you were asked to solve for in the problem, now you can get that. Okay? Oh. And then what are all of the forces we should be looking for to label on our free body diagram? So most of you already know these, but there is just a nice little mnemonic device you can use to remember what they are. So if you think about when you're doing your free body diagram, you want the forces. So if you look at that, that's going to be weight, or the gravitational force. Oh no, I hit the button. I'm sorry. Which is mg, and then A for the applied force. N is the normal force. T is tension. And then F is friction. Right? And if you don't know it off the top of your head, that friction formula is mu times the normal force. And that's mu sub S or mu sub K. So the coefficient of static friction or kinetic friction. All right. And if you get those mixed up, you can think of like S is for stay and K is for kinetic, which if you think about the word kinetic, most of us know that that means motion in some capacity. And we'll learn more about kinetic when we get to like kinetic energy, but that's the energy of motion. So it helps you think about like movement. So if it's moving, it has kinetic friction. If it's staying put, it has static friction. Okay. All right. So any questions on the Newton's second law problems or the forces? We'll give it a minute for the stream to show me if you have questions or not. Okay. I don't see anything, so I guess that's a no. All right. I'll check it again in a minute. Moving forward. All right, so problem one. Now we actually get to do problems. So that was our review. Oh, you know what? Hold on. I promised after we got done with the review, I'd show you the index card. But let me go ahead and pull the index card up and show it to you. So this is my index card that I made last year. I didn't have time to make a new one, but I just kind of read out the parts that are not on your test. So the kinematic stuff is under the red box, but we're not doing that this test. So I have my unit conversions up here. Which are really my metric prefixes. I don't know why I labeled it like that, but so I have some metric prefixes up here that I just might not know off the top of my head. I didn't put G on here, so if you don't know that G is 9.8, you should put that on your index card because you'll definitely need that. I've got my free body diagram forces here. That way, when I'm drawing my free body diagram, I can look back and make sure I get them all. I put my steps for the Newton's second law problem. I wrote my Newton's second law here, and then I drew myself a little diagram about how to break a vector into components to make sure that I do it right. To just kind of remind me on the test. All right, so that's just an example of what you could put on an index card. And again, I've got a whole bunch of extra room here, so if I wanted to, I could copy like whole homework problems on there or something. All right, what size index card can you bring? There is no size requirement. So Dr. Chastain is not requiring you to have like a 3x5 index card. He's not going to walk around and, you know, check how large your index card is. So you can bring it as large or as small as you want. So whatever you've got at home is just fine. Now he does not want you to bring in a poster board. So, you know, an actual index card, but any size you want. And you can use the front and back of that. So if you get, I think the largest one I've ever seen is half the size of a sheet of paper. And so you effectively have a sheet of paper front and back if you use the front and the back. So the things you don't need are the equations he has in the flowcharts on the, yes. So the flowcharts from week 3, I believe, those are the kinematics equations. So you don't need to have that. Because the kinematics is not going to be on the test, but you would need to know like Newton's second law. All right, Keeley says, make sure you have the FK equals mu times Fn formula on there as well to swap into the equations for Newton's second law. That's exactly right. If you don't just know the frictional force law off the top of your head, you should put that on your index card. I did not put that on my index card. That is missing on mine, but I also have that memorized, but I just didn't think about it. So if you don't know that off the top of your head, you should definitely put that on your index card because you will need it for sure. Okay. Gabe says, where can I get an index card that big? I honestly have no idea. Yeah, I would say Staples probably has got various sizes of index cards, or maybe Walmart or something. Kroger doesn't have a very great selection of office supplies, but Zach says tape a bunch together to make like the ultimate Franken index card or something. I mean, I guess that's an option. Yeah. But yeah, there's no size requirement, so you can go find one. Gabe, I'm not sure where you would find one by now because it is 7 o'clock at night, but Walmart's 24 hours, right? I think Walmart might have it, maybe. Yeah, I do. Yeah, I agree. So Keely said Staples or Office Max. I agree that your best bet probably would be an office supply store that would have multiple sizes of index cards. But I mean, it's a very large index card. But you know, if you feel like you really need it, go for it. I mean, I use probably like what, maybe about half an index card here. But I mean, I also don't have the frictional force law, but that doesn't take up that much space. So, you know, so there's that. Roll out a giant sheet that's just F equals MA in big letters. If you want to do that, you can. All right. So are you guys ready to move on to questions? Oh, Warren says that there's a room in CP that has a bunch of index cards. I don't know if those belong to someone or not, but if they're free and just there, go for it. Okay. For unit conversions, do you just need to know those 6? So those 6 prefixes are the most common ones that are used in this class. So you might not even see them on the test, but those are just good ones to know in general. And that's why I have them on my index card. Gabe says if he tattoos equations, will that count as part of his index card? Well, technically, no. That would then be you. Petunia says, do we need to know any conversions for American units to metric? That I don't think so, just because for the most part, he's going to give you a question in units, and he's going to expect you to report your answer back in pretty much the same or similar units. Most of the time conversions I think that you guys have had in your homework and problem sets or in class have been time conversions. So like he might give you a problem that has like a mixture of hours and minutes, and he would expect you to convert all of that into hours. But I don't think he's not going to make you do like feet to meters or like miles to kilometers. I don't think he will do that. But if you want, I mean, if you're concerned that he might, just put it on the index card. Yeah, I also don't think there's a requirement the index card be handwritten. So if you can't read your own handwriting, or you just don't like your handwriting or something, you can type it and glue it on there, and I don't think he cares. All right, so we'll move on to the next section. All right, so a box is sitting on a table that has one end gradually raised. When the end of the table is lifted 4 meters, the box is about to slide. So just ignore that. That should be a 3, because this is 3 here. Okay, the book is just about to slide down the slope. Right, so the first part we're going to do is label the forces acting on the box, and this basically is your free body diagram here. So if I'm doing that, then of course, so if we want to go through our checklist, so our checklist starts with weight. Sorry, I'm like moving my pages around. Okay, so our checklist with, whoa, oh, hold on, there's a lot of messages. What is this? Oh, Gavin says, do we get a calculator and does it matter which kind? Yes, you can use a calculator, and no, it does not matter which kind. So as long as you have something that is considered like a scientific calculator or more advanced than that. So you need to have square root functionality, and you need to be able to do trig and inverse trig functions. So like sine, cosine, tangent, and inverse tangent, of course, because you're going to use that when you do your vectors. So if you walk in with like a basic calculator that just has like the plus, minus, and whatnot, that's not going to help you much, because you're not going to be able to do any of the crazier stuff with it. But scientific graphing calculator, like I've got a TI Inspire, and that's fine. You just can't have, like, you can't use your phone as a calculator, because that can access the internet. So as long as your calculator doesn't access the internet, you should be fine. Yeah. And yeah, so Zach pointed out you can put notes on the calculator. So if you know how to do, calculator programming, and you want to type some stuff in there, that's fine, because you just decided to put it in your calculator instead of on your index card. Okay. All right. So label forces acting on the box. So our little checklist, right? So if we think about our checklist, well, let's screen that up. Okay. So weight. So it's going to have an mg. Oh, hold on. Wait, my bad. So the mg is actually kind of at a weird angle here. So it's going to kind of come off that way. Yeah, and this one, if you guys are drawing it and pretending like, if you want to kind of like rotate that and make the box kind of turn, that's fine too. So I'm just kind of drawing it like it's right side up. Okay, so we have our mg and applied force. In this case, we don't have one. Our normal force is always perpendicular to the surface, so it would come up there, right? Tension, we don't have a tension here. We don't have a string or anything holding that up. And then friction is going to always oppose motion. So this book is going to slide down the slope, and that means that our friction is going to point up. Okay, does that make sense? If it doesn't mention friction in the problem, do we assume there is none? So it's actually backwards. So typically, if friction's not mentioned, you just kind of assume that there is friction. And then if it says the word frictionless, then you would know to exclude friction. So it'll say frictionless or ignoring friction. Or sometimes, like if you've got something on ice, we tend to assume that the ice is frictionless for this class. But it'll usually say it on there if it's not friction. And if there is friction, you're just going to assume it's there unless told otherwise. Okay. All right. So there's our free body diagram. And then if we want to think about this, we're going to have to chunk our gravity up, right? Because, oh, I should put this on here. So acceleration is going to be down slope because it's sliding down the slope. So it's going to start off kind of just in place, and then it's going to move very slowly. And then as it continues down the slope, it's going to pick up speed. So our acceleration is going to be down slope. So that means that our axis is going to be like this. So our normal and our frictional force are already along the axis, but our gravitational force is going to have to be chunked up. Right? And if we look at this, so if this is our theta, and this goes down, it's going to make a right angle here. So that means that this angle here is 90 minus theta. And then if we look at this axis, it's going to come down. This is another 90-degree point. And we can see that this part is part of this 90 minus theta. So that tells us that this angle here is going to be theta. So it's going to be on this inside portion, and it's going to be connecting to our y-axis. Why is gravity pointing diagonally? Oh, so this box is actually at an angle. So the gravity does go straight down, and it's right here. But with respect to this being like our y positive and x positive axis, it's going at an angle. So I've taken the box from here and I have rotated it and put it over here. Does that make sense? Could we have drawn our mg vector pointing the fourth quadrant? That is the fourth. This is the fourth quadrant. It's in right here on the right side. So like alternatively, you could have had your box like this. Well, I guess if you could have done your point like this and had your mg down, and then had like your normal at an angle and your friction like this. It's the same thing as this. I've just taken this and I have rotated it theta degrees to the right or left. Do you need to prove on the test why theta is theta with respect to gravity? No, as long as you put your theta over here, you'll be fine. But if some people have a difficult time trying to figure out where the theta goes, and they might put the theta up here. So that's why I was going through the steps of how you know it's on this intersection. Another thing you could do is if you're pretty confident that there might be an inclined plane problem, you can just kind of put that on your index card. That way you know that that's where the theta would be for an inclined plane, and you can put that on your test. So you do want to include where theta is probably on your free body diagram. That way when you go to make your table, you can reference it, but you don't necessarily need to go through all the steps like that on the test. You can if you want to. It's safer to do it than to not do it to make sure you got it right. Okay. So that's my free body diagram. And again, I basically just rotated it a little bit and now it's upright. Okay. So once we get that, so label all forces acting on the box. We've done that. So next part, with the positive x-axis put a down slope, which we already did. Write two equations to represent Newton's second law in x and y just before the box begins to move. So if we're looking at just before the box begins to move, that means we do not have motion yet. Okay. Oh, okay. So the third quadrant, it's not in, it shouldn't be in the third quadrant because that would mean that it was going off this way. So it shouldn't be going off in that direction because it was down, and that ends up being the fourth quadrant when we set up our coordinate axis. Mary, can we decide not to reference or draw an acceleration vector if there is no acceleration? Yeah, if there's no acceleration, then you don't have to draw it on there. For this problem, it starts off not moving and then it will start moving. So since I know it's going to start moving, I went ahead and drew it on my diagram. And so another thing you could do on the test is you might want to go ahead and just kind of read through the whole problem before you start solving it. That way you know what you're going to have to solve for. So since I already knew that the block was going to start moving, which that was already kind of alluded to here, the book is just about to slide down the slope. I know that at some point there's going to be an acceleration going down, so I went ahead and drew it. Okay. Does that answer that question? All right, so we'll start with the table. All right, so looking at the table, and we're just going to make sure we get all of our forces on here. So we have our normal force, we have our frictional force, and we have our gravitational force. And our normal force is just in the positive y direction. So we have a 0 here for x, and I'm just going to leave the n in the y direction. And then for friction, that's only going to be in the negative x direction here. So I'm going to go ahead and put my negative sign there. And at this point, you can either put the f sub f here, or you can go ahead and put your frictional force law. So I usually will just go ahead and put this here. So I'm going to put my mu sub s n, because this is just before the box begins to move. So if it's just before we started moving, that means I have static friction right now. All right, so I'm staying put, I have static friction, and I have no y component to that. Right, and so next I'm going to look at my gravitational force, which we already kind of determined what's going on here. So I'm going to look at my vector, and my angle is going from my vector to the y-axis. So that tells me that the y-axis is going to get the cosine here. All right, so that's in the negative y direction. So I'm going to put a negative, and then that's going to be mg cosine theta, because I'm going from my vector to the y-axis. Right, and so if the y got the cosine, then that means the x is going to get the sine. This is in the positive x direction, so I'm going to have just an mg sine theta. Okay, and then I can write my sum of forces down here. So in the x direction, at this instant in time, we do not have movement. So my sum of forces is going to be equal to 0. My acceleration is 0. And at the same time, y, also, I have no movement in that direction, so each of these is going to be equal to 0 because I'm at rest. And once I get that figured out, now I can write my two equations. So I'm just going to go straight down the x and straight down the y to get those equations. And Dr. Chastain likes it if you go ahead and write your little summation part here. So I'm going to say that my sum of the x forces is equal to 0, and my sum of the x forces in this case is going to be mg sine theta minus mu sub Sn. And that's equal to 0. And I'm going to do the same thing with the y. Okay, so I'm going to have n minus mg cosine theta is equal to 0. And that's it. That's how we set that up. So it's pretty straightforward once you get the hang of it. And once you get your table set up, writing the equations is a breeze because you're just going straight down that column. And then in this one, I just ended up switching the terms so I would have my negative on the inside. All right. So any questions about the free body diagram for that inclined plane or how we set the table up? Does it matter if you leave mg as the force of gravity? Are you saying like at what point? Because I just have mg in here. Are you saying like over here where I have the f sub g? You could put an mg there, and that's the same. It's the same thing. So yeah, you can just use mg for gravity. If I think that's maybe what you meant. I'm not sure. It's a little hard. It's easier if I can like talk to you guys and see what's going on, but okay. Oh, all right, cool. Fantastic. All right, so next, use your equations from part B and the frictional force law, which in this case, we already used the frictional force law when we put it right there. So we already did that. I'm just going to highlight that. So frictional force law was the step where we put that mu sub Sn in. to solve for the coefficient of static friction between the box and the table. So that's what we're looking for. So coefficient of static friction. Okay. Can you use F sub S for static friction? Absolutely, yes. If you would like to use F sub S for static friction, you can. That's fine. You can pretty much whatever naming convention you want to use. There are so many different ones that, all, it means the same thing. So whichever one that you want to use, as long as you're consistent, you pick one and you stick with it for the whole question, you'll be just fine. So. All right, so using the equations from B and the frictional force law. All right, so I'm going to do this part of the process. So now that I've got kind of multi-part problem happening, I'm going to switch colors. So I did this part in black. I'm going to switch to blue now for part B. That way you can see what's different. Oh, Hallie asks, it's 0 because it's stationary, right? Yes, so since it's stationary, it's been at rest for a while. The velocity is 0, and there has been no change in that velocity yet. Then the acceleration is also going to be 0. Okay, so I'm going to do part C in blue. All right, so first what I'm going to do is, since I have this, I'm going to look at my x equation, because my x equation is what has this mu in it, and that's what I want. And right now my equation has really 2 unknowns in it. I know, actually really 3. I don't have the mass, but that's not going to matter in a minute. So I don't have enough to be able to solve this problem at the moment. So what I'm going to do is I'm going to use my y equation and solve it for n so that I can take whatever I get and plug it in to this. All right. So if I do that, that's pretty simple because it's equal to 0. And I'm just going to see that n is equal to mg cosine theta. So if I put that into my original x equation, I'm going to get this. So mg sine theta minus mu s mg cosine theta is equal to 0. All right. So once I get here, oh, there's questions. Okay. What are all the formulas you need to know for Newton's second law of problems? So you need to know that the gravitational forces and mass times the gravitational constant, which is usually going to be 9.8, at least on Earth, 9.8 meters per second squared. And then you need to know your frictional force law. And I think the rest of it tends to work itself out because you're mostly, if you have an applied force, you're usually either going to be given that or asked to solve for it. Same with tension, you're going to be given that just straight up in units or asked to solve for it. There's not really a formula for that, just by itself. But friction does have a formula, so you need to make sure that you know that friction is equal to the frictional coefficient, so either mu of S or mu of K times the normal force. But those two are the important ones. And then, of course, you need to know that F equals ma. The sum of forces is equal to mass times acceleration. Okay. So once I get this problem, I'm going to notice 2 things right off the bat. I have an m in both terms, and I have a g in both terms. And since I have a 0 over here, I'm effectively just going to divide this whole equation by mg, and that's going to get rid of my m and g. And that's a good thing because I don't actually know the mass. So the mass canceling out is good because that's one less unknown that I have in my equation. So once I get rid of those, I just see that the sine of theta minus mu s cosine theta is equal to 0. That means that mu s cosine theta is equal to sine theta, which tells me mu s is equal to the sine theta over cosine theta. And for those of you who also know that, that's equal to tangent. So tangent is sine over cosine. So that's going to be equal to tangent theta. So the thing with this problem, and I don't think he would do this on a test, but this problem, I just gave you the side length here. So I told you that you have 4 meters here and 3 meters here. And with that knowledge, that tells me that since tangent of theta is opposite over adjacent, that means that the tangent is 3/4. So again, that's just trig. And he will probably actually give you an angle number, but I didn't do that on this problem. And I know that 3/4 is 0.75. So that means that that will be my coefficient of static friction. And remember that the coefficient of friction, since that's actually a ratio, it is unitless. So that is a unitless quantity. We do not have to put a unit on that. Everything else you're going to want to make sure that you put units on. But that we don't need units for. It's just going to be 0.75. Is friction force law always equal to 0? What? Where do you see that the friction force is equal to 0? Oh, ignore that? Okay, I will do so. Okay. All right, so I ended up getting 0.75, and again, that does not have units. Okay, so any questions on that? If not, I'll keep moving. I'll start writing the next one, and I'll check the chat again because there's a few seconds. I think it's about 5 or 6 second delay before I actually see what you guys type. Okay. All right. So once the book begins to slide down the table, its acceleration is 4 meters per second squared. So what I'm going to do real quick is I'm just going to straight up copy and drag table because I have this ability. Come on. Here we go. Paste options. Well, why'd you put it down there? That's not what I wanted. Never mind. Whatever. It's fine. So, I don't know why it didn't like that. Why did you go all the way down here? There we go. All right, so I'm just going to move my table down here so I have it. Oh, hold on. There's a lot of numbers. Whoa. Okay. I have to scroll now. Okay. Yeah, so 0.75, it just comes from the tangent. So since I know that my opposite side was 3 and my adjacent side was 4, I just did 3 over 4 to get that. Well, I mean, you can solve for theta with that. We were asked to solve for the coefficient of static friction, so we didn't need to solve for theta. You actually don't need to know theta in this problem because you just have that opposite and adjacent side length. But if you were asked to solve for theta, you could just inverse tangent that to get theta. All right, so for this problem, so I just copy and pasted the table so I wouldn't have to rewrite it for when we set this up because we have to change our equation slightly now. So now that the book has started to slide down the table, it has an acceleration of 4 meters per second squared. So we need to make appropriate changes to our equations from B and solve them for the coefficient of kinetic friction, which is going to be different, right? And you guys remember the relationship between those, this coefficient of kinetic friction is typically going to be smaller than the coefficient of static friction because the object has to overcome a greater force to just start moving. And once it has started moving, it takes less effort to get it to continue to move. But if it stops again, you're going to have to apply more force to get that movement to start a second time, right? So if we are accelerating and we're sliding down the table based on the way that we set up our coordinate system, that means that we have an acceleration in the x direction. Okay, so we're at least definitely going to have to change this to an MA. And I'm going to do part D here in green. That way you can see what color I'm using. Okay, so that means we have an acceleration in the x direction now. In the y direction, since our x-axis is on the slope, we don't have movement there still, since we're still saying our block is still staying along the book or along the table. It's staying along the table. So if it's still sliding down the table, still has contact with the table, that means we have no movement in the y direction. So the only difference here is that we now have an MA, and this is now a mu K instead of a mu N, or instead of a mu S. Okay, so that's all that's going to change. And we're going to solve these for the coefficient of kinetic friction. So remember, N is still equal to mg cosine theta. We didn't change anything in the y direction, so that is still true. So when we do our x equation, our x is now equal to ma, mg sine theta minus mu k times the normal force. So I'm going to put my mg cosine theta in, and that's going to be equal to ma. Okay? Right, and again, we can cancel things out. So since we have an m in every term, we can cancel those out. And again, that's a good thing because we don't actually know the mass. We cannot cancel our g's out this time like we did in part 2 because we don't have a g over on this right-hand side of the equation. We have an a there. All right, Lauren asks, so you know if it's mu s or mu k based off if it's moving? Exactly. So if it's staying put, it's staying, then we have mu s. There's no movement, and K represents kinetic. If we think of the word kinetic implies movement, so mu K is if it's moving, mu S is if it's not. So since the block has started moving, we're going to have to switch our mu S to a mu K. right? So once we get that set up, we can simplify our equation slightly. All right, and again, we are solving for the coefficient of kinetic friction, so we need to get that value isolated. So mu k, almost skipped my g. So mu k g cosine theta is going to be equal to g sine theta minus a. So that's just some algebraic manipulation to get those terms to move. And then I can just divide this by the g cosine theta. So mu k equals g sine theta minus a over g cosine theta. And then all we have to do is plug values in. So once we have an equation where we have the thing we want equals some things that we know, we're just going to plug numbers in and we will get our answer. So again, and in this problem, I said to use G as 10, but on the test, you'll use 9.8. I just used 10 here because it made the number pretty. So, and in case you didn't recognize it, that triangle from the top is a 3, 4, 5 Pythagorean triple. So that's why for the sine, it's going to be the opposite, which was 3 divided by 5, which is the length of the hypotenuse or the length of the table. And then I can subtract the 4 that was given to me in the problem. And then on the bottom, I'm going to have a similar situation. 4 was my adjacent side. 5 was the hypotenuse of that triangle. Right? And then I can take the 5 out, and that becomes a 2. I can take this 5 out. That also becomes a 2. So it's going to be 6 minus 4 divided by 8. And so it's going to be 2 over 8, also known as 1/4 or 0.25. And again, that does not have units because it's just a ratio. So we don't have to put a unit onto that number. Okay, and that is problem 1. All right, so any questions about that first problem? That is a pretty good indicator of like the complexity level that you might have on a test, on the test tomorrow. So being asked to do Newton's second law and solve for frictional constants, that's a pretty manageable task, and it doesn't include kinematics. I just really would like for this to go away. Can you go over here? Yes. Yes. Go away. Okay, fantastic. All right, so do you guys have any questions on that problem? I'm just gonna get a drink real quick. Okay, moving forward. All right, a plane leaves an airport at 9 in the morning and travels 800 miles to airport B at an angle of 36 degrees east of north. The plane later leaves airport B and travels to airport C 950 miles away on a bearing 27 degrees east of south. The plane lands at airport C at 1 p.m. So this is a vector problem because, well, we don't have any bodies to draw a new free body diagram on. We don't have like forces acting on an object, and we're pretty obviously have some distance and direction information that we can make vectors out of. Okay, so this is where we're going to draw a picture in a vector diagram, and they're going to look a little bit different. Okay, so the plane starts off at A. So I'm just going to put an A here. And it travels 800 miles at an angle of 36 degrees east of north. So I'm going to zoom in a little bit. So I'm going to draw kind of like a little axis guideline with north being at the top. And it's 36 degrees east of north. So I've got something in quadrant 1, and it's east of north. So since north was the second, then that is the side the angle's with respect to. So that's the side that my 36 degree angle is going to be on. And then up here is where I'm going to put a B. All right, so that kind of makes sense how we figured that out. So we've got the distance from A to B, it's going to be 836 degrees east of north. So we found north, went from vector to north on the east side. All right, then I'm going to kind of do the same thing up here. There's my B vector. I'm going to draw like a little dotted coordinate system on it so that I can figure out what direction I'm going. It's traveling to airport C, 950 miles away. So I'm going to make a conscious effort to draw this vector longer than the last one, since it represents a greater distance. And then, let's see, we'll post, so 27 degrees east of south. So in this case, east of south, so that means we're looking at this quadrant 4. So we're looking at quadrant 4. And since south was the second word, that's the one that it's going to be referencing. So this is going to be my 27-degree angle to get to C. All right, does that kind of make sense? Can I post the packet with notes on Blackboard? So I'm not technically supposed to post answer keys. It is against reach policies to post answer keys. But the video will be here so you can watch it, and the link's on Blackboard. So I guess technically you can go watch the answers again if you would like to. Right. So here's our, so this is my picture of kind of what the plane is doing. And then if I draw my like proper vector diagram, I'm going to do just my, well, it's really bad, but I'm going to draw my little coordinates, something here. And then I'll have my like y direction and my x direction. So A comes out at 36 over here. And that's going to be the vector from A to B, so I'm going to call it AB. You can call it whatever you want, but I'm going to call it AB. And then from B to C, it's at a 27-degree angle this way. I'm going to call that one BC because it's going from B to C. And it has a 27 here. And then when we're looking at vector addition, right? Because we're doing this vector, and we're going to be looking at the distance from A to C. So that means our resultant is going to be this here, right? So the tail of the first vector that we did tail to tip with to the tip of the last is how we figure out what the resultant is. So our resultant vector is coming out at some angle, maybe kind of like that, about. So I'm just kind of estimating what that angle is when I draw that, and that's fine. Okay, so that's how I draw my picture. And then I am going to go ahead and set up my table up here. So find the distance from airport A to airport C. I'm going to put my table up here in this little block because there's more space there than there is down where I actually put the room to do part A. So I'm going to do it up here. So remember, we want our X and our Y. Yay. Okay. And then over here, I'm just going to put what vector I'm looking at. So I'm going to have vector AB, vector BC. Those are going to be equal to vector AC. All right, so if I look at this, the X component of AB, it's in the positive direction. So is the Y. And since the Y is going to get the cosine, since that's the one that the angle's touching, I'm going to put, so this way, I'm going to put the sine on the X. So this one had a magnitude of 800. So it's going to be 800 sine 36. And then the Y is going to be the same but cosine. So 800 cosine 36. Right, BC, this one's going to have a negative Y component and a positive X component because it's in quadrant 4. And if we look at this one also is referencing the Y-axis. So the Y is going to get the cosine and the X will get the sine. This one had a magnitude of 950. So 950 sine 27. And 950 cosine 27. Oh, that's negative. Let me just scoot it over so I can get a legible negative sign in front of it. And that's in the negative y direction. Okay. And then AC we know is going to have some x component and some y component. I'm just going to call them x and y. Okay. So we can, I'm just going to get rid of these lines that are just kind of in the way. Right. So if we set up equations for that, so x is going to be equal to, we're just going to add these together. So 800 sine 36 plus 950 sine 27. And if we put that into a calculator, I got 901.5. And that's in miles. And then for the y direction, same idea. We're just going to go straight down that column. So 800 cosine 36 degrees minus 950 cosine 27 degrees. And we find that in the y direction, we moved negative 199.2 miles. So next thing is, does this make any sense? So if we look at that, we look like, okay, we probably moved a pretty decent amount in the x direction. We look like we didn't move nearly as much in the y direction. So I'm going to say that those values probably make sense. Taylor says go cards. Yes. All right. So finding the distance from A to C, this is where we're going to Pythagorize. So we're just going to Pythagorize this x and y value that we got. And we know that the magnitude of AC is going to be equal to the square root of the x component, which is this 901.5, squared, plus the y component, which is this 199.2. It doesn't really matter if you put the plus or minus in here with it, because when you square it, it's going to be a positive number anyway. But we can leave it there for continuity. And when you put that into a calculator, you get that the magnitude was 923.25 miles. And remember that for Dr. Chastain, he wants you to round things to 3 significant figures. So I'm going to round that to 923. On the subject of rounding, Cameron, hey, nice name, has asked what I would consider a good decimal point to round off for components. For components, I would, you can leave it as many decimal places as you want to. And the other thing is, even when you're rounding off to your third value here, to your to your 3 sig figs, like over here, there is a certain kind of range of acceptable values based off how you rounded your other ones. So I kept these ones. These ones, I think when I did this, it was like 0.5003 or something. And I was like, what's the point in keeping the extra zeros? And I think that the 2 was similar. I think it was like 213 or something like that. It was just something really small. So I went ahead and just left it with 4 sig figs. And that's fine. But, if you feel more comfortable holding on to more digits until it's absolutely necessary to relinquish them and go down to 3, that's fine. Okay. All right. So we're just going to Pythagorize that. And then at what angle would the plane have to travel to go back to airport A from airport C? So let's look at our picture again. So back to A from C. So instead of actually looking at this AC vector, we're kind of looking at it backwards because we want to go from C to A. I should probably put that in a different color. All right, I'm going to do this one. I'm going to do part B in red. Let me circle that so you guys can see it. Okay, so we're actually going from C to A. So if we're going from C to A, you can look at it 2 ways. Obviously, since it's the same vector as AC, you can look at this angle and recognize that if you were to flip the vector across both axes and have it go up this way, this would be the same angle on this side, or you can go ahead and solve it like it's that angle. But since it's the same vector, the vector is going to have the same magnitude. We are just completely flipping the direction when we look at it. We can use the components that we solved for up here when we were doing part A, and we're just going to apply that direction manually. So I know that, so for this case, I'm going to think about how do I want to report my vector? So how do I want to report my angle? In this case, based off the ones I have highlighted here, so this one would have been south of east. And on this side, this is north of west. So since I want my vector to be north of west, when I do my arc tangent or my inverse tangent, since I want that in reference to west, I'm going to put my x value, my x component, on the bottom. And that's how I'm going to do that. So I'm going to put my 199.2 on top and my 901.5 on the bottom. And when I put that in a calculator, I get 12.5 degrees. And I underestimated how badly I was going to slant my handwriting when I came across, but that's what I'm going to get. So I'm going to get 12.5 degrees north of west. And again, you don't have to report that as north of west. If you would prefer to report that as west of north, and you want to look at like this angle here, then you would just reverse the order that you put these in the tangent function. So you would just switch them here. Does that make sense? So that's kind of how I think about doing the angles, especially with the northeast southwest, is I want to think about how I want to report it. That way I can make sure I put the numbers in the right spot. Okay, so next part, if the plane was at airport B for 40 minutes to refuel and reload, what was the average speed of the plane throughout its journey? Okay, so let's do this in blue. So average speed is distance traveled over time, right? So just total distance over total time. And in this case, the total distance traveled was, the plane went 800 miles, and then the plane went 950 miles. The one, yes. So that is negative. It doesn't matter if you put it in positive, because I'm applying the direction manually. It doesn't matter because I still put west on there, if that makes sense. So since I said I know that this is north of west, and I'm saying that without looking at the number whatsoever, it doesn't matter. Like what comes out of the tangent function is going to be something between 0 and 90. And I'm going to say that 0 and 90 is in whatever quadrant I've identified that it's in, with respect to whatever axis I've said that it is. So I don't have to put a negative into my tangent to get the right answer if I'm applying my direction manually. Alternatively, you could put the negative in, recognize that it gives you whatever 180 minus this is, and then know that that must be pointing in the west direction. All right. Okay, so back to average speed. So average speed is distance over time. So we want to calculate that distance. So we went 800, and then we went 950. And it took us 4 hours to do so, because we went from 9 a.m. to 1 p.m. So that's 4 hours. So if we do that, I ended up getting 437.5. So I'm going to round that to 438. All right. So part D, I'm going to do this in green. The average velocity. So remember, velocity is different than speed, because when we're looking at velocity, instead of looking at distance, we're looking at displacement. So we only really care about our initial position and our final position, and we don't care at all about what happened in the middle. All right, so we're looking at total displacement over time. And in that case, instead of just using this 800 plus 950, we want to use the total amount of distance that there is between point A, which was my initial position, and point B, which is the final position, or point C, I'm sorry, point C is the final position. And we already solved for that up here when we looked at part A. So we already solved for the distance between A and C if we were to just go in a straight line. So since that distance is going to be that total displacement, from going from airport A to airport C, I'm just going to use that value. So I'm going to use the 923 miles that I got in part A, and I'm going to divide that by 4 hours. And that's going to tell me, so this time I got 230.75, so I rounded that to 231. Right? Why didn't I add the 40 minutes in time? So for that 40 minutes, we were just not moving. And so with respect to this distance traveled, it didn't have anything to do with it because it still traveled the same amount of distance. It went 800 and then it went 0 and then it went 950. And for total displacement, we're only looking at initial and final positions. So the 40-minute pause happening in the middle had absolutely nothing to do with that. The 40-minute part is in that question to confuse you, because it is completely extraneous and has nothing to do with the problem. So we don't actually need it at all. Because sometimes you might think that like you might want to take the 40 minutes out of the 4 hours and solve it like everything only happened in 320, but really that 40-minute pause did affect your average velocity, and it did affect your average speed because for a period of time your speed was 0. So you read that and you recognize that it's there for no reason and we don't actually need it, and it has nothing to do with what we're doing because we're only looking at the total time and we're looking at initial and final positions. It's a trick question. I'm so mean. Okay, any other questions on this airplane problem? So again, this is the average kinematics that will be fair game on the test tomorrow. So not the kinematics equations that we covered with the flow chart in class on Tuesday and last Thursday, but actually I think last week in general. So last Tuesday and Thursday and then this Tuesday. But this is the average kinematics. So you need to understand the concepts of the speed and velocity, and that's why we reviewed that a little bit at the beginning of today. All right, so next we're going to look at number 3. So Dr. Chastain specifically said that Newton's second law problems with 2 objects were fair game on the test, and this is a pretty traditional one. So if you have 2 masses that are connected by a string and a pulley, and in this case, see the string is massless, and that's pretty typical because then we don't have to deal with it having its own mg somewhere. And then the pulley is frictionless, and that just means that the friction's not going to directly have anything to do. So, and that basically is telling you that you're going to have the same tension from the block 1 to the block 2. It does not mean that the slope is frictionless. So we're still going to have friction on this mass 1. Okay. And then let's see. So let's go ahead and look at this. So the way that I did these on mine is I put like mass 1 over here, and I put mass 2 on this side of the diagram and did my free body diagrams. So for mass 1, I left this one as, I did not rotate this one like I did on question 1. I left this one kind of catty-cornered. All right, so again, if we want to go through our checklist, mass 1 has a weight that's going to be going straight down, so that would be here if you drew it on the diagram. Applied force, there's no applied force in this situation. The normal force is always perpendicular to the surface, so it's going to come off kind of at some degree that way. So again, that's meant to mirror kind of this action. And then tension, we have a tension force because we have this string, so we've got a tension going this way. And then friction, so again, friction opposes motion, so now we have to think about which way the block's going to move. So if I think about it, mass 1 is 10 kilograms, mass 2 is 30. So mass 2 weighs 3 times as much as mass 1. So I'm inclined to believe that that means mass 2 is going to want to go down. And if mass 2 goes down, mass 1 is going to move up slope. So if mass 1's moving up slope, then my friction is going to want to oppose that, and it's going to want to point down. And that's how we figure out which direction the friction is going to go. Right, and again, since our mg is at a weird angle, we've already identified that this is going to move down. This block is going to move up slope. That means that our a, those are the directions on our acceleration vectors. So since our acceleration is going to go upslope, that's the axis that we're going to want to define that. So our friction and tension are going to be along the x-axis, and our normal force is already on the y. So the only one that we're going to have to break up is mg. I'm trying to kind of draw it like under the friction a little bit so you can see it. Okay, and again, this is a similar situation to what we had on the other one. So if you look at the trigonometry, you'll see that the angle theta will be here. So this will be an mg cosine theta in the y direction and an mg sine theta in the x direction. All right. So that is for block 1. And then I went ahead and did my table for block 1. So we have a normal force. The normal force is only going to be in the positive y direction. We have a tension force, which is in the x direction. Right. Let me make it kind of small. Right. And then friction is in the negative x direction. So I went ahead and put my mu in there. And we can leave that blank for a minute because we're going to figure out if this is actually moving or not. And then mg. So as we said, sine on the x, that's in the negative x direction. And then mg cosine theta in the negative y direction. So that's negative in both components. Right, so there's that. And then in the x direction, let's see, so mass lifting through frictionless pulley. So this is a good time where to look through the rest of the problem to figure out if this is moving or not. Okay, so if we look at part A, this says coefficient of kinetic friction. So that tells me that this must already be moving. So I'm going to go ahead and put my k here, so mu sub k. And then we have an MA in that direction since we have movement, and in the y direction, since it's just going to be moving down slope, or it's going to be moving up the plane, that's going to have a 0. Should probably like move this somewhere so it's not just completely illegible. So it's running into the problem. So there we go. I've moved that up here. There we go. All right, so now let's go ahead and look at block 2. So block 2 is going to be slightly easier. We don't have as many forces going on. So actually I'm going to move this up. All right. So mass 2 is going to have an mg down. No applied force. No normal force because it's not resting on a surface. It's just dangling there. We do have a tension force in the up direction from this string. And then in this case, we're not going to have friction because it's not touching a surface for there to be friction on. So that's it for mass 2. We just have the tension and the m2g. So if we do a table for that one, it's going to be pretty easy because we just have these in different components. So the acceleration is going down. So I'm going to say that that's the positive direction. So I need to make sure I keep track of that m2g. Okay, so there you go. So that's that. All right. So now if I write equations, so mass 1's equations, sum of f sub x equals ma because we have movement along the x-axis. So we have tension minus mu k times the normal force minus mg sine theta equals ma. It's really bad. In the y direction, we have the normal minus mg. Sorry, I started totally just writing that like it was 2 different lines. Whoops. So normal minus mg cosine theta equals 0. And then for m2, we're only going to have an equation for the y direction because we have no movement in the x direction and no forces acting in the x direction. So this one will just be m2g minus t equals ma. All right, so there's our equations that we'll be using for the rest of the problem. And that's how we set those up. So Again, when you're doing multiple masses for Newton's second law, you can identify the axes separately. So this one has got so mass 2 has a kind of traditional, looking coordinate system, whereas for mass 1, we kind of have rotated our traditional coordinate system into more of an X. And that's perfectly fine that they don't match. They can have their own separate ones, and it's fine. Okay. The important thing here is that our tensions are by themselves so that we can set them equal to each other and whatnot if we need to. All right, so find the magnitude of acceleration of the two masses if the coefficient of kinetic friction between the plane and mass 1 is equal to 0.4. All right, so we're solving for A. And remember that they have the same acceleration because they are moving really together. As mass 1 moves down, mass 2 moves up. So since that's going to be the same, we need to find a way to combine these equations. And the way that we're going to do that is by using that tension, because it is present in both, and it's the same tension because it's the same strain. So we're going to combine the equations together using the tension. So if we look at our mass 1 x equation, we see T minus mu kn mu kn minus mg sine theta equals ma. And if we look over at the y equation for m2, let's see, we'll see that m2 g minus t equals ma. So if I can solve this for tension, I'll get that the tension is equal to ma plus m2g. Oh, sorry, there's a minus there. It should be negative ma m2a plus m2g. Oh, you know what? That's the thing I need to be more careful about. I'm really bad about just writing m's and not putting their little subscripts on there. Those ones all have a 1, and then these ones should have a 2. That one did. Okay, I remembered one of them. Right. So make sure you label those. I'm just really bad about that. So, all right, so there's our tension. And then our normal force, if we look at the y equation here, we're going to solve that for the normal force, and that one's pretty straightforward. The normal force is going to be equal to m1g cosine theta. So we can use this tension and this normal and put them into this equation. So it's going to be minus m2a plus m2g minus mu k times m1g cosine theta minus m1g sine theta. And that is equal to m1a. So that's kind of a gnarly looking equation, just a little bit. Let me put that up here. So that's kind of obnoxious. And we're solving for a. So we want to get our a's on the same side. So I'm going to take this a and I'm going to move it over. So m2g minus uk m1g cosine theta minus m1g sine theta equals m1, and I'm going to go ahead and combine this, but since you're going to get m1a plus m2a, it's m1 plus m2a. So I'm going to factor that out to get the a by itself, which means I can write that a as this entire nonsense in the numerator and then simply m1 plus m2 in the denominator. So now that I have acceleration equals a bunch of just nonsense that I have values for, I can plug values into that. So if we plug values into that, m2 is 30, g is 9.8 minus 0.4, so that was given to us for the coefficient of kinetic friction, times 10 for mass 1, 9.8 for g, cosine of 28 minus, I'm going off the page. So M1 again was 10. Actually, let me try to stay on the page, but So minus 10 times 9.8 sine 28. And then that whole mess divided by 10 plus 30. All right, and we should get, if you type that entire mess into a calculator, I got 5.34. And remember to include units, meters per second squared for acceleration. Okay, and that's it. All right, part B is find the magnitude of the tension in the string. You can do this several different ways to get full credit. So you can use any equation that T is present to find the tension. So you can use this mass 2 equation in the y direction, or you could use the mass 1 equation for the x direction as long as there's a T in it, solve for T, and plug values in. I used the mass 2 equation because I thought that that one was going to be easier. It doesn't have any trigonometry in it, so no sines and cosines, and it's pretty straightforward mathematically. So I remembered solving. If you remember, we solved for T up here. So if we look up at, well, actually, so if we look up at this part, and I'll do this in green, where we solve for the tension in part A to put it into the equation, I'm going to use that to solve for T. So I already have it in terms of T equals. So M2A plus M2G. And that's really M2 times, in this case, G minus A. So factor that out. And then mass 2 was 30. So 30 kilograms times the 9.8 for G minus the 5.34 that I got in part B. I'm just going to use that. And when I put that in the calculator, I got 133.8. So I'm just going to round that to 139 newtons so that I have my 3 significant figures that Dr. Chastain's looking for. And that's that. I should probably box both of them then. All right, so that is how I solve for tension. All right, so this is another pretty standard type of Newton's second law problem that might be on the test. So in this case, we're solving for acceleration and tension. The other one, we solve for frictional coefficients. And those are the main types you guys will probably see since we're not doing kinematics. All right, so any questions on that problem? We're just going to keep chugging. We're almost done, guys. We're doing great. We're making great time. Can you believe that this video stream has already been going on for 2 hours? It's insane. We've only been doing physics for an hour and a half of it, but, you know, hopefully you guys feel more prepared for your exam by the end of this. That was the goal. Okay, so number 4. So this is an example here. I've given a Newton's second law problem that does not have a picture already included, so we have to draw our own picture. So 2 masses are joined by a massless rope. A vertical force F equals 30 newtons is applied to the upper mass, which gives the system of masses an upward acceleration of 3.2 meters per second squared. If the tension in the rope joining the masses is 18 newtons, what are the values of the 2 masses? So now I've given you acceleration and tension and asked you to solve for mass. So first off, we're going to draw a picture. Oh, thank you, Taylor. She says she's more prepared for sure and sent a cute little blob face. I've never seen the blob emojis before, but they're kind of neat. All right. So for this one, I'm going to go ahead and draw my picture. So the way I understand it is we have 2 masses and they're joined by a rope. So I'm just going to draw 2 rectangles in a line. I apologize for my drawing abilities because there's really none here. So I have really bad boxes and lines, but it's fine. I make the other diagrams like on here with the shape tool, but it takes a little bit of time. So I'm not going to do that right now. All right. Okay, so a vertical force, so vertical tells me it's in the y direction, is applied to the upper mass. So I'm going to say this has got an F happening here. And it gives them an acceleration. If the tension is joining, what are the bones? Okay, so there we go. So I'm just going to label these mass 1 and mass 2. So there are my masses. And I'm going to draw them each free body diagrams because that's what we do. So 1 free body diagram per object that, oh, Andrea says my boxes are beautiful. Thank you. So we're going to draw our free body diagrams for mass 1 and mass 2. So there's my dots. So for mass 1, I have an mg down. So m1g. So there's my weight. I don't have an applied force. I don't have a normal force because I'm not on any kind of surface. So we're going through the checklist again. T, I have a tension because I am connected by a string to another box. So I have a tension going up, and I have no friction because, again, I'm not on a surface that can give me any friction. So I just have a T, and I have an M1G. So for this one, I'm actually just going to skip the table step because they're only in the y direction anyway. So Fy equals Ma because we know that these are moving. And so that's going to be T minus M1G equals Ma. All right, so there's mass 1. For mass 2, we'll go through the checklist again. Weight, we have a weight of M2G. We have an applied force because we have this vertical force is applied. That's my applied force right there. It's pretty straightforward and said. So we have an F. And then we have no normal force because, again, we're not on a surface. And we have a tension because we are connected to mass 1, and that is down. So I'm going to draw kind of another arrow on top of the first one with the tension force going down just so we can see that there are 2. And same idea here. I'm just going to go ahead and write my equation. So in this case, since I know the object's moving up, which I probably should have put that on here, I know that they're moving up, both of them are. So that tells me that my up direction is positive. So I'm going to do F minus T minus M2G equals M2A. And again, I forgot my subscript on my mass 1 and my mass 1s over on the left. So I'm going to add those. So make sure you add those if you forgot like I did because you were just writing down what I was doing because I'm really, really bad about that. All right. So once I get that squared away, I'm just going to draw a line here to kind of divide what I'm doing. So now I can go about solving for the masses. So this is pretty straightforward because we're not even going to have to connect the equations together. We can just solve for the masses independently from each free body diagram. So for mass 1, we have this equation. So T minus M1G equals M1A. I'm going to move my M1G over. T equals M1A plus M1G. I can factor an M1 out of that. So M1A plus G is equal to tension. So M1 is going to be equal to the tension divided by A plus G. And when I plug numbers into that, I know that, sorry. So when I plug my numbers in, I was told the tension was 18. My acceleration was 3.2, and I know that G is 9.8. And that's going to give me 1.38 kilograms for my mass 1. Right, and then for mass 2, same idea. F minus T minus M2G equals M2A. F minus T equals M2A plus M2G. And same idea, I can factor out that M2, divide by A plus G. M2 is going to be equal to F minus T over A plus D. I know that that applied force was given to me as 30 newtons, so 30 plus 18 divided by 3.2 plus 9.8. And for this mass, I got that M2 is equal to 10.9, right, 10.9 kilograms. I kind of fudged my K there. 10.9 kilograms. So those are my 2 masses. Right, so that one's pretty straightforward. This one, see how short this problem is compared to those longer multi-step ones that we were doing before. Questions 1 through 3 had multiple steps like that. Those are more indicative of what a free response question would look like on the test. This could pretty easily be a multiple choice question. So you could be asked to find the masses, and so you could have like, you know, A, B, C, D, and each of them have 2 different values. And you can figure out which one, you know, whenever you solve for your 2, mass 1 is equal to this, mass 2 is equal to that, or whatever. So this is more lengthwise kind of how a multiple choice question might look for the test. All right, so any questions on that one? I'll start scrolling down to 5. Okay. All right, so 5, an airplane can fly at 300 miles per hour in still air and wishes to fly due west. Right, so the thing that's standing out here is that you see this word wish, and that tells you that that is probably a resultant vector. So wish, desired, and this is setting up a subtraction problem because we have this questionable result. We're told the resultant vector. So that means it must be a subtraction vector subtraction problem, right? There's a wind of 20 miles per hour blowing from the southwest, which is exactly between south and west. Determine what direction the pilot must point the plane in order to fly in the desired direction and determine the resultant speed of the plane. This is a really good vector problem because this is about as complicated of wording as you're going to get in a vector problem. So if you can kind of dissect this problem and get the right information out and be able to solve it, then you're in good shape. Okay. So since it wishes to go west, I'm going to label that as my resultant vector straight west. All right. So I'm going to call that my resultant. And then we have a wind of 20 miles per hour from southwest. So we have to be really careful here because we're coming from southwest. So that means southwest up. So there is my wind vector. I'm going to call it W for wind. And then the plane is going to have to point in some direction in order to obtain this R. So if we're thinking about this like a vector subtraction problem, and we think, okay, so we have this wind that goes up here, and we know that we have a resultant vector going this way. So if you think about kind of the way that we add vectors together, right, we go from tail to tip. So this one's going to have the tail of this vector. And as you're adding vectors, after you get done kind of, tagging each of your vectors together, tail to tip, tail to tip, tail to tip, your resultant goes from the tail of the first to the tip of the last. So that means that the tip, whoa, that was weird. That means that the tip of this vector must be where the tip of the resultant is. So that tells me my vector has to go kind of this way. Okay, so if my vector goes kind of that way on my vector diagram where I want all of them coming from the origin, I'm going to go this way, and I'm going to call that one P because that's going to be the plane's vector since that one is modeling the plane's movement. All right, so that's kind of how we're going to figure that out. I'm going to put this over here. All right, so wind plus plane equals resultant. All right, so now we can just do our table. So if we've set our table up with our X and our Y, is this weird things happening to my screen? Right. Actually, I should probably do I was doing colors and then I stopped. Okay, and so we have a resultant vector, we have a wind vector, we have a plane vector. All right, so our wind vector is 20 miles per hour from southwest. So if we're looking at that, I'm going to say that the angle's here. We know that since it's exactly halfway between, that's going to be a 45-degree angle. If you don't know that halfway between is a 45-degree angle, it's just because each of these corners is 90, so that's halfway, so 90 divided by 2 is 45. And I'm going to put my cosine on the x-axis since I am referencing the x. So I'm going to say this one is 20. 45. Tried to write like the first and last numbers together. And for me doing this, sometimes when I set up my axis, I like to think of like which one's going to have the less negative. So for me, I am going to work this problem with x positive being pointing to the left, just to show that it really doesn't matter which way you point your axis as long as you are consistent throughout the problem. So for me, that wind vector is going to be pointing in the negative x direction. If you want east to be positive x, you're just going to flip the signs on everything x related that I do, and you will get the same values. Right, and then in the y direction, that one's going to have 20 sine 45. That's already in the positive y direction. The plane vector. So the plane vector, we know that the plane can fly 300 in still air. So that tells me the magnitude of my plane vector. Oh, we have a question. Do you know that it was referencing the x because it said southwest and west is the last part? Yeah, you can think of it that way. It ultimately isn't going to matter in this situation just because it's halfway between. So the way I would think of it, so say you had like 70 degrees. So if I were coming from 70 degrees southwest, I would think south of west 70 would probably be here. So south of west would be this angle. And then if I'm flipping that, it's going to come up this way, and that is still going to come down onto the X side. So if you look at the way that those end up mirroring when you're looking at angles mirroring over the axis. So yes, that would still be on, in this case, the east. Could you put cosine on either X or Y? So 45-degree angle is the only one where the sine and cosine are going to be equal. So technically, you'll get the same numeric answer either way. For the purposes of like the way that this kind of diagram works and what Cameron pointed out in the chat, technically that is referencing west or referencing east, and so X should get the cosine. But in just only this one specific case of it being 45 degrees, would that not actually affect your answer? But for practice, I would go ahead and leave it on the X because that's the way that I kind of rationalize where that angle came from. All right, so again, so that 300 is the magnitude of our plane vector. And since I defined west as positive, this is going to have a positive X component, and it's going to be 300. And I'm going to say that my theta is going to be a south of west. So I'm going to say it's with respect to west, and I'm going to have a cosine theta on my X direction for the plane vector. And I don't know what that theta is yet, but I'm going to be solving for it because that is this part right here. Okay, and then in the Y direction, this one is in the negative Y direction. So I'm going to have negative 300, in this case, sine theta. So the same theta value that I don't know yet. All right, and then the resultant, since the resultant wants to go just straight west, then the entire resultant is in the X direction, and I have nothing in the Y direction. Okay? And so this is kind of where really your vector subtraction problems you can work. I usually just work them like vector addition problems because it's the same idea. And you can use the same way, but essentially here, like for our Y equation here, our unknown is actually this second value instead of it being like down here where the red is. And you can still work it like addition because it's, blue plus question mark equals 0, and you can figure out what the green is that way. Or you can think of it like the red vector minus the blue vector is equal to the green vector and solve for it that way. And either way, you should get the same thing. Gabe says, if you kept your axis east, would both of your wind components be positive? Yes. So since in that case, your wind component would be in the northeast quadrant, so it should have a positive X and Y component. Does still air mean anything? Still air just means if it's going straight and there's no wind, it can go up to 300. So in this case, if it's counteracting the wind movement, it just means that like its top speed is 300. So that's just telling you the magnitude of the plane vector. If it did not have any kind of other vectors happening. So if you just straight up were drawing your wind vector and it were just like that, it would be going 300 without any other vectors having to be added to it. Having the wind there, you're now adding another vector to that. And if that vector is going to be counteracting what direction you're traveling in, like this one is, then it's going to mean that you're trying to travel a little bit slower. If the wind were going in the same direction as the plane, it would speed it up a little bit. Aha, yes. It's our aha moment. All right, great questions, guys. Keep the questions coming. I am checking it every few, like I'm looking up kind of while you might hear me kind of like prattling on a little bit when I look up, but there is a little bit of a delay, I think. But that's okay. We're working with it. I think that this is pretty successful. I like this live stream situation. I think it's working out pretty well. Do you guys like it? You can flood with emotes if you like it. Make me feel like a Twitch streamer. All right, I'm gonna write my equations now. Right, so again, back to the steps we use when we're solving a vector problem. We drew our picture. We have our proper vector diagram. So our picture was kind of this weird triangle that we drew to figure out what direction that was going to go. And then we've got our vector diagram here. And we chose our axis and did our table. So now we're going to write our equations. So in the x direction, we're going to have this minus 20 cosine 45 plus 300 cosine theta. And that's going to be equal to r. Yeah, I'm glad you guys like this. It's fantastic. Yeah, it's really cold outside, so this is definitely better than everyone having to be outside and walking around campus with it being completely frigid cold. So I'm pretty happy about that because it means I don't have to be outside either. But I just want to make sure you guys got your exam review because you have a test tomorrow, and it would kind of suck if you didn't get to have any last minute opportunity to have your last minute questions answered and stuff. It's already kind of unfortunate, you guys, because recitation today was supposed to be a review situation, so you guys didn't get that. So at least we have this, right? All right, so there's my x and y equations. And what I'm going to do here, so pretty easy to figure out what the plane of attack is going to be. I'm solving for both the angle and the resultant. So in the x equation, I have two unknowns. In the y equation, I only have the one unknown. So I'm going to use my y equation to solve for theta. And then I can use that theta in the x equation to solve for r. Right, so in this case, I can solve this to get theta. So 20. I don't even know why I did that. 20 sine 45 minus 300 sine theta equals 0. So 20 sine 45 equals 300 sine theta. And divide this by 300 to get sine theta, and then you can just arc sine that. So you can just put that into a sine to the minus 1, so inverse sine this, and you should get that theta is equal to 2.7 degrees. So it's a very, very, very tiny angle. Oh, there's more messages. Plane of a, oh my gosh, Taylor, plane of attack. That's brilliant. Yeah, Kaylee, you're right. That is really sketchy. It would be really dark and really cold. All right, that's 2.7 degrees into our functions. And again, we've identified that theta as being south of west, so we can put that there if we want to. So south of west to tell us where that's coming from. You got 2.6. Yeah, it's really close. It's a very small number. Did you round the sine 45 when you put it in? And also, I did a bad job because that's not actually 3 sig figs. I have 2. But let me check and see what I got real quick. I don't remember exactly what it was. It was something really obnoxiously small. And it being obnoxiously small is correct. All right, let's see. So I got... yeah, I got 2.702. 2.6 is close enough that he would mark that right because it's probably a rounding thing. I did not round sine 45, so I just straight up put 20 sine 45 over 300 in my calculator. Like I typed that all in one. So if you did like your sine 45 separately and then multiplied that by 20 divided by 30 and did an inverse sine, it's going to round it automatically just a little bit. But 2.6 is close enough that would be counted correct because that's pretty... Yeah, there you go. Yeah, so just, I mean, and that's why like a teeny tiny bit of rounding error can change the answer by a decimal point. So don't be too worried about it if you're off by that much because believe me, he knows how much that tiny round can change it. And there's really more like a range of acceptable values. So like he might, for this one, if he knows that like if you type that straight into a calculator, you get 2.7, he might accept anything between like 2.5 and 2.9 or something like that. Like he's going to have kind of a range of acceptable values. It's kind of like statistics. Statistics is the same way. There's like a range. As long as you're in the range, you're good. In the green. All right. Yeah. So I ended up getting 2.7 and 2.6 is just fine. All right, so once I get that theta, I can put it into this x equation to get r. I'm going to move this somewhere because I need that spot. All right, I'm going to use this one x equation here. So 20 cosine 45 plus 300 cosine theta, which now we know is 2.7. So I'm going to put my 2.7 there. and that's going to be equal to R. So if you just type that into a calculator, I got R equal to 286. That is rounded slightly. So again, if you got something kind of close to that, but not exactly, well, my 8 and my 6, well, I just wrote an 8 instead of a 6. That's bad. I do that sometimes. I'll say something, and what I say is fine, and I will write something completely different. There's a disconnect. So I got 286 miles per hour for my resultant vector. And again, that's going to, so it's going to be going 286 miles west, and the plane's going to have to point 2.7 degrees south of west, and that is your final answer. And so any questions on that or on anything that we've covered so far? That's the end of the packet. We timed that almost exactly perfect. This was supposed to be 6:30 to 8:30, so we've got 4 minutes for questions or whatever. And if you've got any questions, just put them in chat and I'll answer them until they're gone. So thank you guys for coming. This is really awesome that you guys came and sat at your computers for 2 hours and watched me work physics problems. So that's really great. If you didn't sign in yet, I'll put the QR code back up for a second. So if you didn't scan in yet, go ahead and scan in and sign in to the session. That way we know you guys liked it. And if you guys really liked this, just send me an email saying that you can put hype in the chat. That's fine, Warren, go for it. If you guys really liked this format, just send me an email and let me know, and I'll kind of collect them and show Reach that they liked it, and we'll see if they want to let me do this again. Physics party. Yeah. Yeah. But I'm really glad you guys like this. I'm glad we were able to get something to work out. So big thank you to Dr. Chastain and to Julie at Reach for setting this up, because I honestly didn't think classes were going to be canceled, and Dr. Chastain just had that nagging feeling, and he was like, we're going to have to figure something out. And Julie helped us out setting me up with the account. So this is really awesome that we were able to put this together at the last minute. I'm loving the emotes, guys. It's great. And again, if you like this, just send me an email and let me know that you liked it, and I'll just collect those and take them to Reach so that they know. Or you can like the video. Oh, you guys did. 7 of you liked the video. That's pretty sweet. I wasn't expecting that. You didn't get the QR code when you signed in. Oh, the QR code is for attendance purposes, so that we know that you came and that you liked this. Well, actually, so even if you didn't like it, please scan the code anyway. So you can scan that. If the scanning doesn't work, you can email me and let me know that you watched it, and I can add you manually, or you can use the link on Blackboard. So I'll show you Blackboard again. So here's Blackboard. This is the SI tab. It's under here under assignments on your Blackboard page. It looks like this. This is my quadrant that's here. And then you can click on this sign in link here, and it'll take you to the exact same survey that the QR code would have taken you to if it's scanned properly. Smash the, oh wow, you guys did smash it. It went up by 10 since I mentioned it. That's pretty awesome. You guys rock. This is great. Yeah, I really like how active you guys have been in the chat. This is really awesome because I can't hear you guys. It's kind of weird. I'm used to being face to face with you. Oh, you scanned in on the Google form? Oh, if you signed in through the Google form and you're there, then you're good. Let me, Bryce. Yes, Bryce, you're in here. I can see your name on the Google form. Okay, don't forget to subscribe to Reach. Oh, you guys are welcome. Absolutely. That's hilarious. Don't forget to subscribe. Yeah, I'm glad you guys like it. Again, if you really liked this, just send me an email and I will let Reach know that you guys liked this a lot, and we'll figure out if we want to do it again or something. We'll figure something out. But thank you guys for coming. You guys have any other questions for me, or probably shut this down in a few minutes? I think the video will stay up, so if you need to watch it again, it'll be there. And yeah, Keely, you're right. We did definitely have more people watching the stream than we normally have in an SI session. It got up to 60 at one point. And then I think, yeah, it's down to 30 now. People have started leaving, but because we're done. But yeah, but there's always more people at a regular exam review than there are at just a regular weekly session for sure. But you guys are totally welcome. I'm glad you guys liked this. I'm glad you guys came and watched it. It would have been really awkward if it were just like me watching myself on the on the video. All right, I'm gonna go ahead and shut the feed down since we're done, and it doesn't look like you guys have any content-related questions. You can keep flooding the emotes because that screen will still be up. I'm just gonna stop the screen share. All right, thank you guys again for coming. I'm really glad that you guys like this, and I hope it helps you. Good luck on the test tomorrow. You guys are gonna do great. I will see you guys on Tuesday. There's the tunnel.